Right, what's up guys? Today we're doing Dasha Code Championship, which has some prizes and stuff. And also, I'm quite excited about the problems today, because the problem setters are, well, Ericto, who does not need any kind of introduction, I believe. And also these two guys, I believe, from this year team from USA for IOI, and I believe both of them got gold medals. I didn't check, but the names looked familiar to me. Right, so we're going for 2 hours and a half, and it's starting now, so I hope it's going to be interesting. I'll try to explain stuff as I go. So let's go and read the problems. Okay. So we need to paint the numbers. Okay. We need to output the smallest amount of numbers, so that should be easy. Because we can paint numbers greedily. And there we go. There we go. That's all it takes, right? So basically we are choosing the smallest number, and then we are allowed to, that should work, then we can have all the other numbers that are divisible by it to the same color, and then we just proceed until all the numbers are painted. Okay, so that should be all we need now. Hopefully I didn't miss anything. Okay, so that worked. Nice. Let's go forward. Okay. I'm sorry if it's too noisy. My laptop is a bit noisy and I don't have a good mic to use. Maybe I'll get one someday. For now we have these. Okay, so we have these patterns. Okay. So we have, it's going to be periodic, with period at most like 260 or 240. So we can just check first few moments. Okay, So how are we going to do this? We can just the maximum number of lights that will be on at the same time. Okay, let's go for 1,000. So then you're going to toggle all the guys that are toggling at this moment. That's what we have to do. If there's one by one errors, and it will hopefully be okay. It will hopefully be cut on the sample tests. Sure, it's unsigned. Whatever. So 2 is the answer here. 4 is somewhat an interesting case here. Do we have other cases? Okay, so 6 is the answer here. How exactly do they toggle? I just wonder. Do they toggle at the start? Yeah. I believe that's all we need. Yeah. I didn't read that very carefully, but it should be fine. Okay. Let's go to the next problem now. We have a sequence of digits. And we need to paint all digits into colors. So that seems to work. Okay. So basically, yeah, we have to find any way to do this. Okay. There is a multi-test. Sure. So basically that means that we are printing all the small digits in the color of 1, and yeah, so basically what's going on is, like, if we have a situation like that, whatever, we could print all of these in number 1, then some number can we go greedy again? No, not greedy, it doesn't work. Or greedy, why not? I'm not greedy. It's basically, if you consider the smallest digits, then we either paint them all or we paint a few of them. Preferably the last ones, well, because that's better. So we can try 2 cases of, well, all cases of which is going to be like the split digits, which will have both colors, and then we sort of have our greedy, I believe. Let's try that. So we have multi-test. We can output any of the valid ways we can. Are we guaranteed that the answer exists? No. That's fine. So now we're trying all digits that we are using. We should be fine with that. Okay, so now we go with the first color. With the first color, we can just do it like that. So in this case, we just skip the digit. And otherwise, there's probably a simple way to do that. Okay, so if the digit is small, then we have to paint it. Sure. And otherwise, we can take the digit, we can take the digit D only if all the other digits are gone. And in this case, there will be no violation. Okay. Now the same thing goes for all the large digits. Okay, except we have to go from the back. Okay. Just do it the other way around. We have to design that. And then we have the non-increase. Yes. Okay. That should do it, I believe. Okay. No? Come on. Let's also do this. Wow. What's going on here? Probably no. Sorry. Oh, I didn't paste the test. Okay. So that appears to be the correct answer. Is there some case I want to try? Any particular case? Maybe something like that. 2, 3, 3, 1, 1, 2. So there is only one solution? Yes. Okay. Do I care about the performance? Probably not. Okay, so let's open that. Alright. So nothing too bad so far. And hopefully it works. Okay, let's go for problem D. This is from the American guys, I believe. Okay, so that worked. Because all the cows and farms, they do use that a lot. Okay. Alright, so basically we have a graph and we have to arrange the edges so that, yeah, basically we can use DFS because in each connected component, I'll explain later, but in each connected component, is the answer just k minus the number of connected? Yeah, so connected. So if we consider a graph, okay, and there is a connected component, if we arrange these pairs in some way, then the first edge will always take 2 snaps, and then we can build these trees so that these guests, these pairs, are not unhappy. And so a connected component of size C allows us to make at most C-1 guest happy. So the answer is K minus N. Okay, so how many guests can we make happy? How many guests can we make happy? Like N, right? Minus the number of connected components, so like that. So this is the largest number of happy pairs. Is that right? Let's try this. So in this case, we have one connected component, so the answer is supposed to be 4 minus 4. So that doesn't work, does it? Why doesn't it work? Probably because there's there is one more component of an isolated 5. Anyway, that's what we're supposed to do. So there's no, you don't have to retrieve the answer. So let's just go with GSU because it's faster, I believe. Like that. Do we have multitest? No. So we're just counting the number of connected components in the graph. supposed to be -1, and then for each connected component we add 1. Okay. So like that. So there's 1, and then it's just a 3, so the answer is supposed to be 0. Oh, okay. Did I miss anything? Probably not. Okay, going forward. Running on pretest. Okay, probably not running. Anyway, yeah, seems to work. Okay, so we can shift columns. Is this just like maximum matching? That's just maximum matching, right? So what's the deal with the hard version? Okay, maximum matching in this large matrix. But it's still maximum matching, right? So we could just go with Hungarian. Am I missing something? For every row, the maximum value. Why isn't it just? Oh, okay. It's not maximum matching because that doesn't exactly work. Okay. You could do bit masks, right? Yeah, basically we could choose any number. We could shift and then choose elements arbitrarily because like we're maximizing the maximum. So if we choose any number, it's not going to exceed that. So we could go for all columns and choose the shift and choose the subset of numbers we're going to take. So that's going to take us like, what's the time limit? Yeah, so that's going to take us like, where's the cursor? It's going to take us like m times n times t to the n. No, 3 to the n. 3 to the n. The test case. But then again, we could just pre-compute for every mask what's the largest value. So that's instead going to be m times n times t to the n plus 3 to the n. So that's a bit better, except that's a bit too much for 40 test cases. So we have to optimize a little bit more, right? Do we really need to have this and here? I don't think we do, because we could just treat all the shifts later. So that becomes t to the nth times 2000. Well, not sure if it's good enough. Not sure if it's good enough. Can we do better than that? Probably not. Not sure. What am I missing? How about we write this, we got this, and then we see how fast it works. Maybe it will just work from the get-go. So we are going for the hard version. Okay. Because if we solve it for the hard version, then we get the easy version for free. Hopefully. Cool. So Telegram, I thought I disabled you. Can you please die? Please? How does it even work? I disabled you. Come on. Okay. Let's save up some time here. And then we just have to like prefix sum. That's going to take like n. We still have n. We still have n. Still have n. Or do we? We probably don't. Yeah, we don't need to do this. Okay. That's also we could go with the built-in function, but probably be a little bit faster to do it like that. Okay. So we have computed this. Now we have to go with the shifts, and the best way to do that would be probably just so that's supposed to be shifting. Okay. The other is not terribly important. Okay. Now we have to hold on. How are we going to guarantee that they do not intersect? Like we don't take the same mask from this two masks from the same column. Yeah, that doesn't work. Jeez. We really don't want to do this. Alright, 3 there, yeah. Multiplied by m at least. That's not what we want. So this is bad. This will not work fast enough. Am I missing something here? Did anyone solve it? Okay, cool. So a few people solved it. Could it be like meeting the middle trick? What to do? So if we take a single element from every column, then it's just n maximums. If we take more, then it's a little bit tricky. It could be some sort of it is a sort of convolution. Except it's maximum convolution, so it doesn't really work all too well. So How much is 3? That's too much. We can do that once per test, but not more than that. So, okay, the global maximum will have to be somewhere. And it is going to be maximum in its row. Let me place it. So what? What about this convolution stuff? Maybe we could still do convolution stuff. Maybe we can get rid of some of the columns. For example, do we care about a lot of columns? Like, if so we can take a look at some of the largest elements, for some number of large elements, for example, I don't know, n squared largest elements. Okay, so if m is larger than that, then at least m minus n squared of the columns are going to contain all the small ones. So for this number of columns, they all have numbers that are smaller than like n squared largest numbers. So are they going to be useful? I don't think so, because if we use any numbers here, then for some reason, actually, anyway, then that means that one of these large columns is free, and so why use that when there's a large number in some of the unused columns? So that's not going to be useful. So we're going to need instead of 2000, we are going to need like n squared is a rough bound. Maybe it's just n. So if all the numbers in the column are less than like nth largest, and it's going to be used, then, well, what about all these numbers that contain these? So some of the first n numbers isn't used, and it's not always that we can use that, because it could be in the same column, but it's important that these large numbers are in the places, and so this number we can't just use that. But still, maybe 2n here? What about 2n? About 2n. I'm just guessing now. What's the correct bound? So for each of these columns containing the large numbers, there is no column with an unused number, without any used numbers. Okay. So how many columns? Or how many numbers, rather? Is it just and columns containing the largest numbers. Oh, rather n, like n plus 1 maybe. So some of them are going to be unused, and so all the other columns are useless. Cool. So instead of 2000, we have 13. Cool. And what now? Should we go 13 times 3 to the power of 12? So how much is that? Times 40. I like that. I like that. Okay. So how about we do that? And let's also have all numbers. So if a column only contains numbers that are smaller than that, then it's useless. Yeah. Also, how about we switch dimensions here? Sure. It was correct, but the dimensions still should be switched. Okay. So this means that no. It's not. It's not what we wanted to do then. Come on. Yeah, that's not what we're doing. So now we're only taking at most n plus 1 columns sorted by decreasing of the largest element. Yeah, that's sort of what we want. Okay. Cool. And then we just do our old thing, right? Probably something like that. Cool. And then we have to convolve this together in 3 to the nth time. Is what we want to do. Cool. How to do that? Should we use another array, or can we go with the old one? We don't want to have like double updates, but if we go like that, we should be fine. That. So supposedly that's what we're doing. We still have to look at the performance of the thing. The answers are correct, which is good. So now let's generate some tests. Which are just random. So here are random tests. Sure. So how fast does it work? What? Why does it work so fast? Did I generate the tests correctly? Why does it work so fast? That wasn't supposed to happen. Did I miss anything? Why did it work so fast? I'm not sure if that's like is correct. What? I'll take that. That's how it's going. So let's try the easy version first. If I get wrong answer, yeah, I know that something's wrong in my solution. If I don't get wrong answer, then it's probably correct. Right? Right. Okay, so let's see the hard one. The hard one. We do have max test there, no? I'm not sure what the reason is for it working so fast. It's like it's faster than a second. What? Cool. Cool. I'll take that. So what other problems? Okay, so G1 is very solvable because again there are two versions with that. People are solving F, so let's go with that. Sure. Also let's check the standings because I want to. All right, so not the best. What's happening? What's happening in the first page? Okay. So I took much more time than a lot of guys did. So on the other problems, I'll have to be quick. Right. Okay. So it's like we have to find the Jesus. Okay. Sure. So we are just okay. We are concatenating the numbers of edges we are traveling, and we want to minimize that number. Cool. So if all the numbers had equal length, that would be easy. It's probably still easy because we want to minimize the length of the number. So we want to find the shortest. Well, to determine the length of the number, we want to minimize the okay. So first we minimize, define minimal length with the Dijkstra. And then what? And we want to if we have, then we can leave all the like good candidates that are like, if we want to determine the first number, then we almost know it, except there are a few cases. Like if you know that the optimal answer here is like 10, and here it's 7, and here it's 8, it's the length, and we have an edge with these numbers here and with these numbers here, and we have to sort of compare what's better, what's going to be better now. Can we split the edges? Okay, I think I know what to do, but I want to think for a moment. If you'll excuse me, I promise I'll be back soon. But before I go, I want to read the next problem so that I can think on both of them. Cool. Sure. So here we have to do that without updates, and here we probably have to do it with updates. Okay, cool. So I have something to think about now, and I'll be back soon. Okay, so is the cam on? Cool. So f is easy. We just have to do some. We have to basically do some sort of BFS, but be careful about layers, and we also want to split the edges, because, well, they correspond to multiple digits. So we're splitting the number into digits, and then well, they're going to be directed, which is important. Okay. So we're doing these chains between the numbers. Okay, cool. So we've created this graph. Now, So in one layer of these BFS, we are taking the last layer of BFS. And then trying to expand forward, and the distance is determined by the equivalence class of the parent and the digit. That's also okay. And then we are splitting all the vertices of the new layer into classes of equivalence as well. Okay. We are storing answers for the equivalence classes. Maybe that should do. Let's see. Okay, so we also have to update the layers, probably. Okay, so most of the answers are correct, except for the last one. Let's see. How about we create all edges? That would be nice. That still doesn't help. Okay. We don't visit the last vertex. It's not supposed to happen. What is not supposed to happen? Do we generate these correctly? I think so. I do think so. That helps. That helps. That helps. Cool. Okay, so we don't need that anymore. Okay, it seems to work. What are the answers? The answers seem to be correct. Cool. Cool. So that seems to work. Let's go. That was easier in my opinion than E. I could run out of memory then. That's fine. So where does it put us? Okay. So let's think about G now. So basically we have to okay, so we want to transform the sequence into this good sequence where it consists of block of equal values. So if t numbers are equal, everything in between has to be equal. So we can, if we want to count the answer for a given sequence, that what we can do is we can construct this graph, sort of, between consecutive equal numbers. And then if two arcs intersect, basically everything covered by this bunch of intersecting arcs, we have to make equal to the same number, and that can be done by, well, if there are these portions where no arc intersects this, then this is the cut between the parts, and then in each part we have to choose the most frequent number. So G1 is easy, and G2 is harder because it's easy to maintain if for a certain position of the block it is covered by an arc with a symmetry, but then maintaining the most frequent number in each of the parts is something that I don't know how to do yet. Okay, so what we can do is we can solve G1 and then sort of go from there. Yeah, I see lots of people solving it. And it's somewhat easy to do as well. Okay. So this is how many numbers we have to change. Difficulty. Okay. Presumably, this should be the answer. Cool. So let's submit that. 5. Okay, so no one solved any of the last two problems, and I know the G2. I don't have any sort of idea, and writing a solution for it would be going from scratch, probably. So let's read the last one too. Maybe it's more profitable. Huh. That's cool. Okay, so we have these walkways, right? So we have this huge segment, and we have these walkways that speed us up, and they also do not intersect. Okay, so basically we have some numbers that are added to our speed. There are zeros in between, and then some numbers for each particular walkway. And so we have energy, and we cannot make it negative, and we can choose the speed with which we walk, and if we walk slowly, then we regain energy. Regain energy. We have to choose our speeds. So this is added to our speed. Okay. So this is interesting. Cool. Sure. Go for it. Yeah, so we should. So how do we distribute our energy? So assume that we want to get in time t to the back. Okay. So what that means is we gain t energy, and like the integral of our speed dt. So let's like let p of x, p of t rather, be our coordinate, and well, the strike of t is our speed, right? So this integral, so the total amount of energy we have is like, not sure what it is. Let's think, if we don't have any walkways, what's the optimal like regime to walk? So if for epsilon seconds we have two intervals of epsilon seconds, if we maintain speed 1 on both of them, then we travel to epsilon units. But if we like save up energy and then spend this energy, then this is the speeds. We have covered the same distance, right? So that means it doesn't matter. Even if something is added to our speed, then we will still have covered the same distance. So that means, what that means is, if we wait and then spend the energy to like double our speed, it's going to be as effective as if we spend this way, but yeah, as long as we are constrained to one walkway. If I'm not making any mistakes here, and I probably don't, right? We still cover the same amount. So this means that for the first part we have to wait, like if we have a segment of length L, we have to wait for L over 2 seconds and then double our speed for L over 2, except if there is a walkway right after that, well, we will wait for at least this amount. But if there is a walkway after that, then we're not sure. We are not sure. We could trade some time waiting to increase our speed. Okay, so basically what we're thinking is it if you're waiting for additional absolute amount of time to double our speed later, so if we don't do that, then we will cover, like if we have v1 and v2. Okay, so we have v1 here, oh, v1 plus we are waiting, right? Oh, okay. I'm not even sure what I'm trying to say. Like, there is this observation that when we are constrained to the segment, we can wait, and that's not worse than like have constant speed. But how does that extend to the case when there are walkways with different speeds? Not sure. I'm not sure. Actually, I'm going to have one more break and think about it. Sorry, I'll get back to you as fast as I can. Right, see you. Okay, I think I sort of figured it out, but I need to. We have camera on. Okay, we have to do some math. Okay, so if we are currently at we want to cover distance of epsilon, and we have this v0 like base velocity, and v is our velocity from 0 to t. Okay, so the time we'll need to cover this distance is epsilon over v0 plus v. Okay, and the energy that we'll gain is time times 1 minus v. Okay, so that's epsilon times t over 1 minus v over v0 minus v. Okay, we don't have epsilon anymore. Okay, so how does t depend on delta E? Well, it just follows that it's I'm done. If we know delta E, how can we determine T? That's the question. So that is equal to epsilon over v0 minus v. Let's rewrite that. Epsilon times v0 minus v plus with 1 minus v minus v. So that's just epsilon, or rather, yes, that's just epsilon plus t times 1 minus v0. Okay, so t in terms of v0 is delta E minus epsilon over 1 minus v0. Okay. So that means like dt is equal to dE minus dL over 1 minus v0. Something like that. Okay. So the L is our parameter. Okay. So let me think about it. We can choose this however we want. Like this is epsilon times whatever we want from this segment. And that doesn't seem to be correct. That's tricky. So to have dt, so t is, oh yes, that seems to be true. Okay. What if v0 is 1? What do we have from that? If v0 is 1, what does it mean? If v0 is 1, then not sure what it means. Not sure. It means that delta E, that E will always change by epsilon regardless how we move. And so it means that we should, no, that's not correct. It's not correct. Oh, it's plus. Okay, that makes sense. So plus here. So that means we'll need a different formula now. We'll need a different formula, okay. So we'll have minus v0 minus v plus 1 plus v0. Okay, so now we'll have minus epsilon, and here we'll have plus. And so this means that to calculate t, we have to have plus here and have plus here. Cool. Cool. Okay. So that means is the time we'll take depends linearly on the speed we take, on the delta E. Yeah. So if we choose to rush, so V is 1, V is 2. If delta epsilon is minus 1, and my head hurts. I feel like I'm close. Maybe that's plus. So, yeah, it's not from -1 to 1, isn't it? But rather, so delta E is the largest we can have is if we rush, and so we have. Is it even monotonous in the? Yeah, of course it's monotonous. If V is larger, then this is smaller. Yes, so the smallest we can have is if we don't rush. So we'll have minus dl plus yes, or rather dE over dl is at least, so divided by epsilon, this will be -1 plus okay, so this cancels out. 1 over Vt, so it's at most 1 over Vt, V0, and at least if we rush, we'll have, oh my god, okay. So if you plug this here, we'll have minus over V0 plus T. Cool. So in this segment, it's linear, sort of. So this is the E over the L. This is the Q. Sort of linear. Okay. So that it means we know what to do now? Not sure. So that means that for a prolonged period of time, we'll have dE, like this segment just expands. And if we have current graph of the smallest E for the current value, the smallest T for the current value of E, it's going to be like this convex function. And then as we take a walkway for a prolonged period of time, that's going to be a Minkowski sum with this segment, so this is going to be pushed outwards, and then some parts of this graph will be in the negative, so we cannot allow that. This is all it takes. Maybe, but the formulas will have to figure it out. Can we get the coding now? I sort of know what to do. Sort of. As long as I didn't mess up the formulas. Still no submissions for the last two programs. Okay. Maybe I know what to do, but I'm not sure. Let's get going anyway. Right. Cool. It's sort of like dynamic programming, except it's like continuous, so we have to do some stuff. Okay. So how are we going to do this? So at the start you have like an infinite slant of 1, and then we introduce this segment, so everything gets pushed to the right. I'm a bit fed up with doing it on screen, so I'm going to figure out some formulas here. So, okay. Okay, I probably made some mistake here. Let me figure it out. Yeah, that seems right. Okay, this makes sense. And this makes sense too. Yeah, I think so. Mm-hmm. Does it mean we can just go like this? How do we go about this? Do we need to cut anything? Yeah, of course we do. Do we just add things, maintain the value at the start? Apparently. So if you plug V0, no, the smallest energy. Like that. Maybe. I'm not sure what is that supposed to be, but that is not the correct number, probably. Okay, so we have V0. Is this the only place where V0 happens? Yeah. I don't know. 0 is not the correct answer. That's not the correct answer as well. Okay, I didn't plug anything. 3 is the correct answer. Incidentally, this is the correct answer as well. What about this? Again, seems like a correct answer. I'm not sure what to make of it. What could go wrong? Nothing. I mean, let's at least make sure that we do something. Well, it's doing something. It's getting some parts out. For all I know, it could be correct. Let's try and submit. We don't have too much time left. Hopefully, map doesn't fail in the end. Maybe this could work too long. So it works on pretests, presumably. Is it really that no one did solve this problem? Well, that's a lot of pretests, okay. How much can we get these to cut? Not too much, right? Okay. So if it works on like 30 tests, it cannot be incorrect, can it? Come on. Come on. Wow, that's a lot of pretests, okay. Is it time limit now? Please don't be time limit. My poor heart won't take it. So what are the tests that these guys are failing? 15. Okay, I passed that. Come on. Okay, so we've passed these two tests. Cool. And it worked pretty fast. And we're in first place now. Ostensibly. I'm not sure. So what about G? What do we make of G? At least let's try and solve it. I probably won't have time to implement it, but anyway. So again, maintaining the cut position is easy if we only want to have the number of cuts. But then we have to maintain like the So if we change a number, and what could happen? We could go with like divide and conquer, like introduce numbers one by one. And so we would only introduce cuts, and but then as we introduce a new number, like we have to merge a bunch of DSUs. We could go with, no, we cannot do that. We cannot do that persistently, at least. I will feel bad if I'm going to be the only one to solve each. Hey guys, like, have you seen my code? It fits on the screen. The whole code fits on the screen. Why didn't anyone like do that? It's like, it took a lot of figuring out and a bunch of formulas, but like, come on. Can anyone solve it? Anyway, so how do we maintain the... Jesus. It feels like DSU. It feels like DSU. But we sort of only care about the extreme numbers. Right? So what does that give us? Not sure. You could go with like security stuff. Oh, here you go. Can I try and hack someone just to get slightly ahead better? I mean, last time I hacked someone, it ended up pretty poorly. But no one seemed to start hacking, and I see a successful hack on B. So how about we try and hack B? Like the idea. Okay, so with hacking, it makes sense to start from the bottom. Is what I found. I don't know about this one. I'm not sure. Can we? I know what I'll do. So this guy does not what I'd like to see. So we can hack him. One is the answer. Is it though? Okay. And so on. Is 120 enough? Because the period appears to be a bit larger than that. Not sure why this works. Is it supposed to work? Anyway. Oh yeah, with prime numbers, we will always get 3. And it's going to be pretty fast, isn't it? Okay, so can we construct a test where this is not true? I'm not sure. We could try. So for 1 and 2, how would we go? Okay. Man. How about we just try everything? These tests. If it doesn't work, we will see that. It does seem to work for some reason. Maybe some other bugs. I'll get back to you. Okay, so this is very consistent. Come on. Okay, so we have here again That's cool. What do we have? We should try different ends. I actually can't tell if this works or not. Maybe it takes some clever construction of sorts. Oh yeah, it's not too hard to do. Okay. How about we try this? I'm sorry. Wi-Fi. Wi-Fi. Why do you have 5? Maybe we should try dealing with this. Still 5. Now 6. Still 5. I see. We just have to be a bit more clever. Here it's not terribly important. So one. Hang on. No. Right. So probably that works. And in any case, the round is over. And well, not like this. Not like this. Okay. I should have been more faster. Feel like hacking this mess. But at least I'm fairly sure that checking 120 is enough. Or am I? Yeah, I'm pretty sure. Because, yeah, the period is... Yeah. I'm being dumb. Okay, well, I was lucky that not too many people solved problem H too fast. So that was sort of a good round, except this start was a bit slow. I believe I explained a lot of things as I went, but in the problem A, if you take the very smallest number and like color it, then you can also color all the numbers divisible by it, and it also always makes sense to do it. And after that, we just get rid of these numbers and proceed until we're done. In B, we just simulate the process for, as it turns out, 120 iterations, and then it's enough because 120 is bound to be a period of this whole process. Oh, maybe 120 plus a little bit, because there's this sort of pre-period. But anyway, yeah. In C, we what we're doing is that, so the color 1 will always include, so as we take the digit, the color 1 will always include all of this, some smallest digits. The color 2 will always include the entirety of some larger digits, and then there's going to be some digit which is like, some of them are color 1 and some are color 2. So we'll try all options for this middle digit, and then we'll go from left to right and color all the small digits because we have to, and then some of the remaining, like these threes, like here, if this middle digit is 2, we have to color all ones, and then we will be able to color the last 2, but not the first one because it's like before the ones, so we can't do that. And then we do the same thing but backwards and color with color 2. Okay. So in D, I've sort of explained the whole process. If you view these pairs as edges of a graph, and then consider a connected component of the graph, then if we take any spanning tree of the connected component, then we can always satisfy all these edges by choosing by taking all of these edges first and all of the others going after that, and then all of them will be satisfied if we take the first edge to be like some of the edges in the component, so x and y. So this guy will take both of them, and then we will choose the order so that it kind of propagates from the edges. And so that every guy, when we take it, the other endpoint of this edge is going to be free. So that's it. So E1 and well E2, I'm not sure. E1 can be solved in some easy way. E2 can be solved in this basically n times 3 to the nth time per test, and that's apparently fast enough, by which I mean really fast. The first consideration is that if we sort the columns by decreasing of the maximum number, then only first n plus 1 columns matter. Because if we assume there is another component and we take some number in it, then why did we take it? We can, out of these first columns, one is going to be unused, so it's not going to use any of the numbers in it, and so instead of this number we can shift it in some way and then use the maximum number here, and it's larger than it's here. And then it's just standard stuff. For each subset of rows, can I make this larger? Okay. For each subset of rows, we calculate maximum sum, and then it's just some standard convolution. Okay, F. I didn't explain F a whole lot, but what we do is we transform each edge into, well, it's a bidirectional edge, so we want to transform it into a sequence of directed edges by creating new vertices, and to account for bidirection we create these chains both ways. Okay, and then we do this process. We sort of do a BFS on the new graph starting from the source, and so we separate the vertices by distance, and also we separate them into equivalence classes, where, well, the class consists of all the vertices with the same answer, and we will compare classes if the answer is smaller, but we won't compare the answers directly. We will only compare the numbers of classes. So if you have the separation of the last layer, like Li, into classes, then we can consider all outcoming edges, and then all new vertices that we haven't visited before are going to form the new class. And, well, how do we assign classes to the new vertices? First of all, we're going to say that the answer for the vertex is going to be, well, it could be like the whole huge number, right? That's obtained by concatenating all the digits, but instead we're going to say that it's the number of class of its parent, and also the digit that we use to come here, to come to this vertex. Okay, so if the shortest path to V comes from this P of V and uses digit G, then this is what's going to be the answer. A sort of a compressed way, because the classes are, well, if you compare classes of two different vertices, then they're equal if and only if the answers are equal, and if they're not equal, then smaller class means smaller answer. Okay, so the cool thing about that is that we can also store this pair as a distance, and then just update it as usual, update it as a pair, compare lexicographically, right? So the class, if the classes of two different options are different, so if there's another candidate for a parent, so the class of these corresponds to the answer of getting from here to the source, So if the prefix is smaller, then the whole pair is smaller, regardless of the digit, and otherwise we have to compare the digits. Okay, and after that we obtain this whole new layer, and then kind of like in suffix array construction, we sort these pairs and separate them into equal groups. Okay, and so all new vertices which have these pairs equal have equal answers, and they fall into the same class. And since we've sorted, the classes are still, the increasing of classes still means increasing of answer. Okay, so G1 is easy. It's basically, as I've explained, somewhere above here, right? So we have these arcs between equal numbers, and then we find these cuts which are not crossed by any arc, and then in each segment we find the most frequent number and change everything in this segment to this number. And I'm not sure how to make a solution of the full problem with this. So H has a lot of math, but you can see that the solution is very short. Basically, what we're going to do is we're going to pretend we're solving this with dynamic programming. And so when we've traveled some part of the way, some part of distance L, we want to maintain this graph of if we have this amount of energy when we've traveled this far, what's the smallest time that we could have that? And we argue that this graph is going to be partially like what's it called? Okay. So the parts of these are just linear functions, and it's convex. And then you figure out how to process. If you have this graph and you have a walkway with a particular length and particular velocity, then you sort of have to find the Minkowski sum of this graph with this linear function, which is bounded. So the bounds can be computed from these parameters, and the slope can be computed from these parameters. And so Minkowski sum in this case means that we, in a way, can I move this to the right? Okay. So if we sort of have to merge these. So what happens is this gets inserted somewhere, but the parts get moved to the left and to the right. And so what that means is some of the parts get into the negative energy, and so we have to cut them off. Okay, so we maintain basically a sorted list of these parts of the linear functions, and then go from left to right and cut out some parts of that, because we know the shift. And that's it. That's basically what it does. So map is a fancy way of storing these sorted parts, and there are some formulas, and in this cycle we get rid of these negative parts. And well, T0 is the answer, and T0 is the height of this point, or rather this point. And we have to recalculate it on every step when we move it, because we cut something. And so anyway, okay, so the system testing is on. I'm not going to wait a lot on when it's all judged. So I'm going to end the screencast now. I hope you had fun. I certainly had. I like the problems. So great job, problem setters. And yeah, let me know what you think in the comments, and see you next time. Right? Bye bye.